You are invited to imagine, discover, and explore by taking part in STEAMfest 2021, an online event starting January 30th that is free and open to the public. Explore scores of engaging hands-on activities in science, technology, engineering, arts, and mathematics, including science experiments, art projects, building challenges, outdoor adventures, and live stream events. This year, online activities have been created by students, parents, teachers, and a range of sponsor organizations, including NASA, Google, several popular YouTube creators, businesses, and a number of community organizations. Join us in this family-friendly celebration by sharing on social media and with family, friends, and coworkers, sponsoring or creating activities, and of course, register your children to participate as STEAM explorers.
Good morning, everyone. Welcome to STEAMfest Live. My name is Lee Blakely, and I'll be your host today. WSTEAMfest.org has over 100 free and fun hands-on activities in the areas of science, technology, engineering, arts, and mathematics. Youth K through 12 can register at WSTEAMfest.org, complete activities, log the results in your journal, earn badges, and win prizes. Today's presentation was organized by Dr. Geraldo Vasquez, a teacher at Woodlawn School. We're grateful for his efforts in making this event possible. We're fortunate to be joined today by Dr. Alvaro Labiano, who is an associate researcher on the James Webb Space Telescope project. I'm going to hand it over now to Dr. Labiano.
So, hello everyone. STEAM, and Woodlawn School, of course, Lee and Gerardo for inviting me. It's really a pleasure to share a bit of my work and hopefully get everyone as excited as I usually am about it. So I think this is my second online presentation, so please bear with me if I have some troubles, sharing my PowerPoint and things like that. But I mean, everything should work smoothly. But yes, it's my second online presentation. I'm still. So I'll share my screen now. If I can make it work. Yeah, there you go. So this should be working. Telescopes that are the ones we are used to, but also satellites, radio telescope, any telescope you can think of needs thousands of people involved and tens of countries. So it's really a worldwide effort. So also I have to thank you, my colleagues at Centro de Astrobilogía, where I work, because they were nice enough to lend me a few of their slides. I work in a big team, so I will be using a few of their slides. And let me start by just showing a picture of the sky. I'm sure everyone has at some point looked up in the sky and seen these kind of pictures or these kind of images. We see a few stars. We see this cloud here that we know it's the Milky Way, the galaxy where we live. A galaxy is basically a bunch of stars and gas and dust joined together and rotating around each other. So ours is called the Milky Way, which is this guy here, and the rest of these points are stars. There could be a few planets and many galaxies. There are many galaxies and nebula, like those extended things on there. Now, with modern telescopes, we can get images like this one. This is Saturn. This is Saturn observed by Hubble, and we can see also an aurora happening on Saturn, right? This is one of the faraway planets in our solar system, and you can see levels of detail that we could hardly imagine even a century ago. We see these clouds, these lines here are clouds. We could see some storms. These are belts of rocks, namely like the asteroids we see close to Earth or when they fall on Earth. So these rings are made of those kind of rocks. We can also go beyond our solar system and obtain images like this one. These are called a planetary nebula for historical reasons. It has nothing to do with planets. This is a region of gas and dust. If I remember correctly, it's through the Orion constellation. And we can see that stars are being formed on all these clouds. Okay, and Our solar system would probably be something like this big. So just imagine the size of this guy here, right? And this is all this gas is collapsing and moving away at thousands of kilometers per second and collapsing and forming stars. And we have all sorts of processes going on here. And we know this just based on the light we get from this nebula. And we collect that light with telescopes, and that's how we do astronomy. Now, before I go on, when I talk about telescopes, I always like to ask the question, what's the first telescope we ever used in humanity, in history? And of course, you will get answers even from astronomers, from some of our friends, like, well, the Galileo telescope, the Newton telescope, or these Mayan telescopes, and right. And this is a tricky question because, of course, the first telescope we used was our eyes. For millennia, we have just looked up in the sky with our eyes, and we did really great astronomy just with the bare eyes, looking up in the sky for thousands and thousands of years. Now, talking about what we're closer to our current telescopes and instruments, I just collected a few pictures. Of course, there are hundreds of examples. Here on the top left, we have this Mayan observatory. It's not a telescope, it's an observatory because it doesn't have the tube with the lenses, but it's a building they used to follow the seasons, track the sun through the sky, right, and such. So do astronomy. A little more advanced than with the naked eye, but it's again astronomy. We have the Stonehenge stones here, which are aligned north to south and east to west, following the spring and all this summer, the spring equinox, the summer solstice, all the seasons, movement of the sun, movement of stars. So also another way of building an observatory. We have a stellar map and sky map with the moon and stars. This is thousands of years old. I forgot exactly how old it is. I would say like 20,000 years old, but I can't remember the exact date. And also, well, I always to remind myself that Asia, I mean, it's probably my problem, but I always think of astronomy, I think of Western world, Europe and USA, but Asian, especially China, has had one of the most famous astronomers in history, in antique history, right? They were the first ones to record, for instance, the explosion of a star, a supernova. And we know when that happened because we can go back to the papers from the 17th century from Chinese astronomers that recorded, well, a bright star has appeared in this galaxy and we don't know what's going on. And now we know that's a star that exploded and created what we call now the Crab Nebula, and it's thanks to the Chinese astronomers. So, but why work on astronomy? Why all these people observe the sky? Because they didn't have our tools, so they couldn't talk about the origin of the universe, or how the Big Bang, or all these black holes, all these things we talk now. So until probably like 1,000 years old, 1,000 years ago, astronomy was mainly related to follow the seasons, predict what was going to happen on Earth based on the sun position, the moon position. The tides are related to the moon. Also, of course, these zodiacal constellations, and astrology. Well, in antique history, astrology and astronomy were the same. Now they are different. I will not get in that discussion unless raised during the questions. So that's what astronomy was mainly used. And of course, with that, as we advance in the science and in the instruments, we went even further and started talking about the universe and black holes, galaxies, and all these things we now hear almost every day about. Also, astronomy has, until very recently, and I'm talking probably on tens of years ago, astronomy was used to keep track of time. Okay, these are pictures of the Paris Observatory in France, and this is in Madrid, where I'm based. So here you can see the light coming from the sun, and as the sun moves across the sky, this spot will move on the floor, and it will cross this line at some point. And this is the meridian on Paris. So when this spot is exactly centered on this line on the floor, we know it's noon, we know it's 12 o'clock. And that's how we have set our clocks for hundreds of years. this in Madrid. This is the observatory in Madrid that shows how we get this kind of lights through this high window. This is the inside of the room where you can see the black window here, illuminating this telescope, and we can measure the height of the sun or the height of the stars. And with that and some alignment tools, we set these clocks. Okay, these are historical clocks used again for centuries to keep track of time. And when you are going on a ship to, say, cross the Atlantic Ocean, to know exactly your coordinates, of course, you didn't have GPS. So to know where you were, you have to look up in the sky, see how high the sun was, and then compare with the clock you had on your ship, and it will tell you how far east or west you would be on the surface of Earth. So again, you have to compare the height of the sun with your clock. But that clock, I mean, we're talking about 16th century, 17th century. So those clocks are not like the ones we have now in our watches or in our phones. Those weren't as precise. So you have to keep synchronizing your clocks with a time reference. And that time reference was what the observatories were having here in this clock. So if I was the captain of the ship, I would go to the Royal Observatory, check this clock, and synchronize mine with it, and then I would take it to my ship, and I would use that as a reference to know where I was on the surface of the ocean. And GPS satellites work on the same basis. Okay, they have to keep a very precise track of time. Of course, the technology is different, but the idea is still there. You really have to know the exact time to know exactly where you are on Earth, on the surface of Earth. So as I said, it was until, I think decades ago, but for historical reasons, it is still the observatories, the astronomical observatories, the ones in most countries responsible for keeping track of time. And this is a capture I did yesterday of the US Naval Astronomical Observatory, where you can see this is the main web, and you can see here that they have one of their tools and the services they provide is the precise time. They have what they call the master clock, and this will give the official time in all the time zones in the US. Okay, and as I said, they use it also for GPS timing, and of course they are not observing the stars anymore. We use what we call cesium or atomic clock, which are incredibly precise. They are so precise that we have to adapt them to what we measure on Earth, but then that's a whole different story. But anyway, so they have these cesium atomic clocks, and they are still responsible for the official time and prediction of seasons. When does spring start? You will go to the astronomical observatory, and they will tell you the exact moment and second where spring or summer starts. And as far as I know, this happens in most countries. In Spain is the Royal Observatory, in France is the Paris Observatory, in the UK is the Greenwich Observatory, and they are the ones responsible for keeping the track of time. But now going back to the telescopes, I have to talk about this guy here. This is Galileo Galilei, looking up in the sky with his telescope. And the reason this is relevant is because he is the first scientist to look up into the sky using a telescope. The technology for telescopes was there. There were lenses, there were people sort of working with these kind of things. Of course, we know in boats they would use them to look to search for nearby ships. But Galileo Galilei was the first one to collect all that technology, put it in a quote-unquote tube, combine the lenses, and look up in the sky. And when he did that, he literally changed our view of the universe. So this is in early 17th century, where there was still a debate of if the sun was rotating around Earth or it was Earth rotating around the sun, and where were we in the universe. So one of the things that Galileo saw was this drawing here. This is a picture of Jupiter, and he saw that there were two bright spots. Sorry, the mouse is too sensitive. There were two bright spots on the right side. And then he observed, I don't remember, I think it's a week later or a few weeks later, and there were three spots and two were here. And then he kept doing this exercise, and he saw that these spots were moving all over the place, up to 4 of them. He could see 4. So he derived that these spots were moons, like ours, rotating around Jupiter. So the whole universe wasn't rotating around the Earth. There were rocks rotating around other planets. Of course, this had a huge impact on religion and on philosophy, but that's a story for another time. He also saw that Saturn, the planet I saw at the very beginning with the Aurora Boreal in South Pole, had these kind of bright things that looked like diffraction, like an effect from the lens, right? But these were real, and he saw that some time later, this has grown to have that shape. And of course, he didn't know what those were. And now with Hubble, with those pictures, and we see that these are rings consisting of all these rocks rotating around Saturn and such. He also observed the moon, and he saw that how depending on the moon, Earth, Sun orientation, the shadow on the moon will change. He also could picture some craters. Here you see the crater with the shadow, and he just followed all the phases of the moon. So he basically opened our eyes to the sky. And that started a race to build bigger telescopes and more powerful, like this one from 200 years later. This was designed by William Herschel, a famous astronomer and scientist. This is about 10 meters long and 60 centimeters wide. So basically 10 times wider and probably 10 or 100 times longer than the one Galileo used. So the science multiplies also by those factors. The deeper we see, how much we collect depends on size. So just see the size. I mean, basically a human will be this tall, right? So you can get an idea of you can see windows here from other buildings, so you get an idea of the size of this beast. This was 200 years ago. We have kept developing the technology for telescopes. Sorry, my computer is still behaving a little slow. Okay, there you go. And these are some of the most powerful telescopes we have today on Earth. These are 8 to 10 meters wide. Remember, the Herschel one was like 60 centimeters. So this is 100 times larger, the mirror, and the size. Well, on the size you can see a car here. Okay, so you get the idea of how big these beasts are. This is in South Africa. These two are the Geminis. One is, I think, is in the US, and this is in Chile. The Keck in Hawaii, the Canary Islands one here in Spain, and also this I love this one, which is the large binocular telescope. It works like the normal binoculars we would have at home. It combines just 2 telescopes into one. So all these telescopes are on Earth. Okay, we can just basically walk up to them. So there's a problem when we observe from the Earth, and is that I'm getting a lot of noise. I don't know why, background noise. Okay. So I was saying, when we observe from the surface, is that we have the atmosphere, right? All the air above us, and we know that there's wind, there are turbulences, there are many effects that vary the density and the shape of the atmosphere. Concerning astronomy, what that creates is that if I look to a star that should be fixed in the sky, right, it will deviate the light that I'm getting in my telescope, and this is a real image. I will see this behavior. If I'm looking to a fixed point in the sky, I will get this kind of behavior, this kind of images. So this affects my images when I observe with a large telescope, because if we have to observe for a long time, so I will get basically a big blur right here instead of a sharp image of a star. Okay. Oh, sorry. I think I just skipped one too many. And that's good. Yeah, sorry. Okay. Yeah, again, my computer's a little slow. And that's where adaptive optics come into place. We want to correct the effects from the atmosphere. So what we do is we point a laser, and this is a real picture, okay? We point a laser up to the sky, to the high levels of the atmosphere, and we create a star with this laser. The same way you use a laser pointer in a presentation or in class, that you just point to somewhere and the dot appears on the wall. We do that same exercise with a really precise, really powerful laser. We do that exercise on the atmosphere and create that little dot on the higher layers of the atmosphere. So now we know how we created this dot, and we can follow how it's moving. So with incredibly fancy technology, we will start moving our mirrors. We'll change the shape of our mirror by 100 times per second to compensate for this movement. Okay? And with that kind of technology, this is a picture of the Uranus observed by the Keck Observatory, an 8-meter class telescope with no adaptive optics. But once we turn on that laser and start transforming the shape of our mirror, we get this kind of images. And you can see the level of detail, just compare one. I mean, we see the blur, we see some rings also in Uranus. We can see a bright spot here, but once we turn on the adaptive optics, we see all those little spots that we know they are storms on the higher layers of the atmosphere of Uranus. And we can see let's compare, we can resolve different rings around it, and we also see the spots there. Now, there's another way of getting rid of the atmosphere, and it just go up in the space. So, this is the Hubble Space Telescope. I'm going to focus on basically 2 space telescopes. Now we have tens of them, or we have had tens of them, but I think Hubble was probably, in its time, the most revolutionary telescope we've ever built. It was launched in the mid-90s, and it is still operative, and it's incredibly hard to get time to observe with it. Okay, basically 1 out of every 7 or 8 applications can get some time. Okay, one out of every 10 people that want to observe with it can observe with it. So it's incredibly hard to get, because the science we can still do with a 30-year-old telescope is still revolutionary. Just to give you an idea, this is the primary mirror. This is the mirror that goes here. It's a 2.5 meter wide mirror. This is basically the size of a school bus floating around the Earth. So if we compare an image from Earth with the same object observed with Hubble in the late 90s, this is the differences we can get. It resembles the adaptive optics, okay, but you can see how blurry this is, and we can see even arms of the galaxy, we can see star-forming regions, we can see dots, we can see background emission from probably another galaxy or faraway stars that are not even present here. So, and the technology of Hubble has improved, because we were lucky enough to be able to go up there a few times to update the instruments and improve the lenses and such. So we've gotten even better images, like the one of Saturn I showed at the very beginning. I'll show also a few pictures at the very end. One of the most revolutionary discoveries Hubble did, among many others, is this one here. So basically, I think it was around the year 2000, Hubble pointed at this weird triangle in the sky. And if you can see in your screens, it's mostly empty. We can see 2 stars here and mostly nothing else in there, right? This is towards the Ursa Majoris, the big pair of the Ursa Majoris. And we were looking for a really, really dark place in the sky. And we just let it observing for about 40 hours, continuously over 40 hours, to see if we could find something else there. And this is what we saw. Okay, in that dark region of the sky, we are literally seeing thousands and thousands of galaxies. We can count over 3,000 galaxies. Of course, you have to go very deep in the image. This is a capture of a JPEG, but if you get the real data, you could see thousands of little points like this, and 90-something% of them will be galaxies. This is a star, but you can see a spiral galaxy right there. And this included the most distant galaxies ever observed by any human, of course, and they were discovered by Hubble just by looking at a dark portion of the sky for 40 hours. Now we've continued observing in this field with more telescopes, and deeper observations, longer observations, and still we are using these called deep fields to understand how the universe was formed, basically. Also, with a galaxy, again, a galaxy is basically a bunch of stars and gas joined together and behaving in the same way together. You can see it's a stunning picture, but the science we can do is related to the resolution we get. So you can see almost well, see some stars and individual regions where they are forming stars. We can see the shape of the dust. We can also almost look into the nucleus. Okay, so we can do incredible science, like thousands of papers with images like this and data like this, not just the image, but data like this. There's of course more to it, but just to give an idea. Also, as I showed earlier, this is a zoom into the planetary nebula where we know stars are forming. You can even see and also guess how the wind is blowing from the star. You can see dust and tails and how everything is being shredded into pieces due to the winds created by the stars and the interstellar medium around it. Also, you can see some background stars, and well, this is also stunning science to be done. You can see the reflections here from the star behind the cloud. So, again, stunning. Now, Hubble is still doing revolutionary science, but it's a 30-year-old instrument, so the technology has advanced a lot. And of course, we keep building bigger and better telescopes, not only on Earth, but also in space. So, right now, the most ambitious telescope, space telescope ever built is about to fly. It will be launched this fall, probably by Thanksgiving. And it's called the James Webb Space Telescope. James Webb was the NASA administrator when during the Apollo missions, so in memory of him, this telescope was named. So it's sort of the successor of Hubble. Of course, the science is going to be a little different, but it's probably the most ambitious space telescope ever built. It's a joint project, as I said, of many countries. It's the US, Canada, and I think 10 up to 15 countries in Europe. The budget is stunning. It's over $10 billion. It took over 20 years to develop. It's going to be the largest telescope ever placed in space, right? It's so big that it doesn't fit in the rocket. We have to fold it and then unfold it. And the science we expect to do with this guy is incredible. For instance, it could observe the light of a candle on the surface of Jupiter. Okay, just imagine you're holding a candle on Jupiter, and this guy could take a picture of the flame of the candle. And this is the real thing. Okay, this is the mirror on Northrop Grumman in California. This is the mirror. This is the solar shields. Of course, we need to block all the light from the sun if we want to observe very faint distant objects. So it will unfold all these shields to block the emission of the sun and the Earth. And all the light will be collected by this guy here, which we call the primary mirror. There's a secondary mirror up top here that will unfold this way. So the light will reflect on the primary mirror, the secondary mirror, and go through this hole here into the instruments that are on the back. Just to give you an idea, this is 11 meters wide, 24 meters long, and 21 meters high. It weighs only, quote unquote, only 6.5 tons. I mean, a 6.5 meter telescope on Earth will probably weigh hundreds of tons or tens of tons. So the whole thing with the spacecraft is 6.5 tons. It has 8 little mirrors, 1 meter wide mirrors, that combined we make a bigger mirror. They are covered in gold, but it's a thin layer of gold, so don't think of incredibly expensive layers of gold. I think the cost of the whole surface of gold is less than $2,000. Okay, if you put all the gold together, you can make barely a golf ball. So, well, $2,000 is a lot of money, but compared to the $10 billion that the whole mission cost, is literally nothing. It will have 4 instruments, 4 different cameras to observe the sky in infrared. So it's this light that is below the red, right? With our eyes, we see from the red to the violet, and we know there's light coming also in other wavelengths, in other colors. And what's beyond the red, we call infrared. So that's where the James Webb will be observing. And it will work at what we say is 50 Kelvin. That's minus 220 degrees Celsius. Okay, so right now on Earth we are around 300 Kelvin. So this guy will work at about 50. So it's 200 degrees less than what we have here. It will go even down to 7 Kelvin for the mid-infrared, but again, that's another story. So it will also travel 1.5 million kilometers, about 1 million miles, to get far from the Earth, to a very dark and quiet place in space, so you can observe distant objects with no contamination from the Earth or from the influence of the Moon or our atmosphere and such, to get rid of all those effects I was showing. So this is a detail of the mirror. These are the 18 segments we call the 18 hexagonal mirrors that create the big primary mirror. There's a hole in the center, so the light can go through to the instruments, right? This is the primary mirror. It will illuminate the secondary where I'm having my mouse, and it will go deep to the back to the instruments. By comparison, this is the Hubble mirror. Okay, remember the mirror Hubble was the size of a school bus. Okay, this is 2.5 meters. This is 6.5 meters. And this is a picture that I really like about how bright and how great these mirrors work. You can see the reflection, right? It's incredible. This is without the gold coating, and this is with the gold coating on top. So as I said, this telescope is so huge that we have to fold it. And this is a picture of the Ariane rocket where we are going to launch it. And you can see the guy is completely folded there, right? Not even all the mirror is deployed. You can see it's folded to the sides, right? And the sun shields will be also folded on it, because otherwise we cannot put it in a rocket and launch it to the sky. And I have a picture here of how it will fly. Okay, this is the James Webb folded. You see the mirrors on the sides, the sun shields also folded up here, so you can fit them in the rocket casing. Now there's a problem with that, and is that we don't want the telescope like this when the telescope fully deployed. So once we launch it, you will have to start automatically deploying and folding the 5 sun shields very slowly, very carefully. If one breaks, we cannot use the telescope basically. You also have to unfold the primary mirror, secondary mirror, also the solar panels that are on the bottom here. So the whole thing, this 20 by 11 by 20 meters wide, basically the size of a tennis court, has to deploy and unfold by itself during 2 weeks basically perfectly, or we cannot do the science we want. And it will. And this is technology we've been testing for. That's one of the reasons it's taking so long to develop, because we are making sure this technology works. So why bother do all this and build this fancy telescope? Well, as Galileo did and Hubble, well, the astronomer, and also the telescope did, James Webb is expected to change our view of the universe and what we know and all the science, and discover even things that we cannot even think of. So there are 4 main science goals, but of course the kind of science we can do is still to be discovered, probably 50% of it. The first main goal, that why we are building James Webb, is to basically understand how the universe formed. Okay, we are going to try to see the first light ever emitted by the universe. This first light and reionization phases. Okay, this is related to cosmology and how the universe was formed. So we expect James Webb to detect it, or at least give us hints of this first light and how the universe was formed. We are going to look at the universe when it was incredibly young. Now it's about 15 billion years old, and we'll probably observe it about a few 100 million years old. So really deep in space, really deep in time. Also, we expect to observe the assembly of galaxies. What's this? This is how the first galaxies were ever born, okay, were ever formed. We know that the universe formed in such a way with this Big Bang, matter expanded, but at some point started collapsing and forming galaxies. We are hoping and we expect James Webb can observe these galaxies, these first galaxies ever formed. That's one of the main goals of James Webb. Also, how stars are formed. We know we have a theory of how stars are formed and planets are formed, but it will give us, James Webb will give us deep insights on all the physics about how stars are formed and how the first stars were ever born and built in the universe, also for the planets. And last but not least, it will detect exoplanets, planets in other solar systems, and hopefully life. And I'm not talking about pictures of green guys on other planets, but traces of life on other planets, like it has the atmosphere, has oxygen, or how does the traces of life look in the atmosphere of a planet? And those are the kind of things that James Webb will be able to detect, and through that guess if there is or there has been life in some of those exoplanets. And that was basically everything I wanted to talk about. I'm happy to answer any questions, and I will leave you with this Hubble ultra deep field, which is the evolution of the deep field I showed earlier, because we keep pushing the frontiers on these fields in the sky. Thank you very much.
Can you bring your Skype back to the foreground?
Oh yes, sorry, yes. So let's here stop sharing.
Bear with me, they're just seeing the bear with me, they're just seeing the All right, so we're going to open the floor to questions. If anybody wants to post to the chat. I know we've had a few comments here. Sajjan wanted to say that this was a great and very intriguing presentation. I'm also going to see if I can get Dr. Vasquez on. I'm going to open the floor to questions. If anybody wants to So we have our first question from Sajjan. He says, how long will it take for the telescope to get into position and unfold and be able to see the first photos?
So for the telescope to get to the orbit where it's going to stay, it will take roughly 2 weeks. Now, we have calibrated the telescope. We know how it works, but things can happen in space. So we will have to, once it has unfolded, we'll have to make sure that it's operating as we expect, and basically that everything is working as we want to. And we'll do that through this calibration phase that we call commissioning. And that commissioning phase is so complex that it will take us 6 months to calibrate the whole telescope. So after 6 months, it will start doing science and getting these great pictures. And I know NASA has a program that's dedicated to literally create great pictures and send them to the press and to the general public. Of course, they are going to be stunning. So it's 2 weeks to get to unfold and get to where it's going to work, and 6 months for us to make sure that everything is great, is working as we expect. Oh, Lee, you are muted.
So our next question is, will the telescope be in one place for the 6 months, or will it be orbiting around something?
So it will be orbiting around a point in space that we call L2 for some, well, Lagrangian point 2. That's not relevant. It's just it will be rotating out a stability point, and that whole system will be rotating around Earth and around the Sun. So it's not going to be still on the same spot. And one of the things that rotation will make is that we will not be able to look to the same part of the sky along the year, right? If we have the Sun, I mean, just think of the Sun and the Earth, and then we have the telescope on the other side with the shields blocking all that emission, so you can basically only look away from the Sun. So as it rotates, it will look to other places in the universe.
Sajin continues. He wants to know, if it's in one place, isn't there a huge chance of collision with another object in space?
So it is not in one place, and we know where we are sending it, so it's a very clean region. And also, even though there are billions of objects in space, the space is so vast that the distance between them is huge. So it's really, really, really unlikely for the telescope to collide.
We have a question from Violet. She wants to know, what if a piece of a mirror breaks? What do we do?
So that's one of the differences with Hubble. Hubble is close to Earth, quote unquote close, so we could send astronauts to fix it, and that's what we have been doing for the past years. James Webb is 1 million miles away, so we cannot send anyone to fix it. And even if we could, it would be so expensive, it would probably not worth it. So if the mirror breaks or one of the segments, say, fails while it's unfolding, we can still do science, okay? Because it's just one part of the mirror. We cannot collect as much light as we would like to, but we can still collect a lot of light and do great science with it. It will be affected, but not so much.
Our audience is worried about the risk and potential disasters that could happen. Saya wants to know, what happens if the telescope does not open up all the way? Is there a way to control it or fix it?
So we are going to keep track of well, I must say, everyone working on James Webb is worried about that, okay? So the great thing about that is that we are so worried, we are making sure everything is going to work and double and triple checking everything. And that's why it's taking so long to launch. Oh, sorry. That's why it's taking so long for us to launch it. And we are in control of the telescope. So it will be moving, we'll launch it and it will basically moving by itself. But all this unfolding happens automatically, and we can control it. We can say, stop this part or start this part and go over through this process. Okay, we send commands through the antennas all over the world and to control the telescope. Or we can repeat the process. Wait, just imagine if it doesn't unfold properly, and we fold it back, and then we can try to unfold it again and see if there's a mechanism failing. All these fancy, very expensive space missions have what we call redundant mechanisms. So it's basically the same mechanism twice. In case one fails, we can use the other one. Of course, if both fail, we are in trouble, but it's highly unlikely.
So Kate has a question. She asks, will it burn up in the sun?
No, because we are sending it away from the sun, right? So it's the sun, the Earth, and then we're launching the James Webb on the other direction. If we would launch it to the sun, yes, of course, but no, we are launching it away from the sun. And it's really far away. So,
does the sun interfere with your ability to make observations?
Yes, absolutely. That's why we have these sun shields, these folded aluminum-looking surfaces on the bottom of it. So we have to block it. Just imagine if you are holding a match or a candle close to a light from a stadium or a car, right? You would see the light, these super bright lights, and you cannot see the very faint candle by it because it's so bright. So it's the same with the sun, say a galaxy behind the sun. We have to block the light from the sun so we can observe the faint objects around it.
Will the telescope be able to look at the Earth, or is it only looking out at the universe?
It's only looking away from the Earth because we want to block the sun and the Earth light for the same reason. So the sun shields, we call solar shields, they are blocking also the Earth.
I'm going to add Dr. Vasquez in here, and hopefully we won't have too much echo because I think he might want to ask some questions also. So.
Alvaro, I just want to thank you for being on this first broadcast. And one question I'd like to ask you is I know that for anything that the reason that actually the delay of what is the reason that this project took so long to build? Because we know, and the other thing is like about talking about the partnership between the ESA and NASA. Just wildly, yeah.
Yes, so it took very long because with the technology was the state of the art. We had to develop new technology to be able to do James Webb. So that's really hard to predict how long it's going to take. And also very hard to predict how much it's going to cost. So there were some budget issues also along the way that NASA had, I don't remember exactly how much money reserved, and then they realized that to build this kind of, say, solar panels or the mirrors, we would have to spend more money or to keep all these thousands of people working, right? So there were budgetary issues there. But the main reason is the technology. Technology is so advanced that, I mean, if you don't know that what technology you are building, I mean, you will run into so many problems at some point that it will take a long time to build. And also concerning the partnership, this mission and any telescope, any modern telescope built is so big and so expensive and requires so many people involved that not one country can afford to build it by itself. And also you may not have the whole expertise of the whatever you are building. And you may have the best, say, optical engineers and astronomers, but there may be some people at University of whatever in Europe or in Asia that has the expertise on building this kind of detector. So you want to get them on board because those are the best detectors. So you create a consortium to work with them and some agreements. And what, you give me this detector, you can observe with the telescope for this long, or I can pay you this money, and then you get all these contracts. So it's kind of things. And basically, not a single one country has all the expertise to build such advanced telescopes or to plan the science. I mean, you need experts on the science to design. I mean, we don't build the telescope just for the sake of it. We want to do science, so we have to know the challenges of the science we want to do and get those experts on board. Like, can I observe the furthest distance in the universe with a 6.5 mirror and 4 instruments in the infrared? And you need some guy that can say yes, and you need to go this deep and collect this much light, and you cannot do it with a 5-meter telescope. So you need really people from all over the world.
Thank you, Alvaro.
I think you are muted again, Lee.
Yep.
Yeah.
We've got a couple more questions coming in here. So Sajin, he apologizes for having so many questions, which we don't accept that apology. We want your questions.
Exactly.
He says, is there a camera on the telescope? And if so, what type of camera and how large is it? And Saya would like to know, what is the gold on the telescope for?
The gold. Sorry, the gold. The
gold color?
Okay, oh, the gold. Yeah, okay. I wasn't sure if what was the goal of the telescope or what was the gold. Okay, so we do have cameras on James Webb. I mean, we don't have cameras like sort of a webcam to see what's going on James Webb, but the telescope has the mirrors, and then that light has to be collected by a special kind of camera, like the one we would have on the cell phone, but these are different because they have to observe in the infrared and they are really advanced. So we don't really call them cameras. Basically, we can call them cameras, but we just call them instruments because they are so sophisticated. They go beyond a camera. Okay. There's one that we call the near infrared camera, but it's incredibly advanced. And the size of all these instruments will be probably like 1 meter wide, 1.5 meters wide. I mean, they have to fit in a rocket, and when you go to space, you have to keep it everything you launch very small and very light. So you have to optimize everything in your instrument to be incredibly light. And yeah, incredibly small, because if you're gonna fit it in the rocket with all the other instruments and the spacecraft and the communication antenna and the solar shields and the solar panels and all that, so you have to keep it really, really, really small. So probably about 1 meter wide are the instruments, more or less.
There we go. So the next question.
Oh, sorry, I didn't answer about the gold. Sorry, I just realized I didn't answer about the gold.
Yeah, please go ahead.
Yes, so we need gold. So the mirrors are not made of gold, okay? They are made of beryllium, which is this fancy material that we can fold into mirrors, and it's really light and it's great for the building mirrors. But we need to put a coat of gold on top of them because the gold is great for reflections in space. Basically, it's a great material. It's a very reflective material. This is very treated gold, very clean gold, and it's a very thin layer of gold which reflects incredibly great. As you could see in the pictures I showed, the one with the guy with the flashlight, you could see how it was almost a perfect reflection. That's why we are using gold. And we only need a really thin layer on top of it.
So Sajjan would like to investigate cost and budgets. He'd like to know how much the cost for the telescope is and how that compares to Hubble.
Ooh, yeah, great question. So the current cost of James Webb, or the budget, the budget of NASA is $10 billion. Okay, then you have to add the ESA contribution and the Canadian contribution. So it will be something about $11 billion, lower than $12 billion in total with all the contributions. I don't remember the cost of building and launching Hubble, because then once it's launched, you have cost of running the telescope and hiring people to operate it and make sure everything is working. So these costs are up until launch. So I don't know what the budget of Hubble was, and of course this was 30 years ago, so it's hard to compare. But I remember that the James Webb, when it was designed, the budget, which probably was higher than Hubble, was around $1 billion. So I would say likely it's more than 10 times more expensive than Hubble, comparing just the figures, not how the dollar evolved and comparing the same figures for 30 years ago and now. More than 10 times more expensive, probably.
Wow. How many countries are involved in the project, and how many people?
I cannot come with exact number. I'm working mainly on one of the 4 instruments, and we are, I think, 12 countries with 18 or 20 institutions in total from the different countries. Institutions, I mean universities, research centers, and that's for one part of one of the instruments. So tens of countries again, probably 30 countries could be involved, 20 countries in the whole just in the instruments, on the science instruments. Then you have other parts being built, like the communications and that. So, but I think that's mainly done in the US. So around 20 countries. People, thousands. Okay, in my team, we're probably like 30 or 40 people right now, but we've changed over the 20 past years. And we're building one part of one of the instruments. So you start multiplying by that, and then you have you need someone to build the mirrors and to code them. So thousands of people, literally thousands of people. And over the past 20 years.
So we've got time to ask. I think we've got maybe one more question here. Let's see. The question says, what happens to the space compartment that takes James Webb into space after or during the time when it's unfolded?
So
go ahead.
Yes, so it goes on top of a rocket, right? I think I showed the picture. It goes on the very top, on the head of the rocket. And basically the rest of the rocket, the rest of the machine is just engines and fuel to launch it to space, right? We need a lot of energy to get rid of to go away from the Earth influence, the gravitational influence. So we are burning all this fuel with these fancy engines, and then those start separating from one another, and they will fall back on Earth. And then in the end, the James Webb is wrapped in a casing that will break in two. Well, it will separate in two. It doesn't break. We plan to break in a certain way. So it breaks in two, and those pieces fly away, and at some point will most likely fall on Earth, but they will burn on the atmosphere. So they will not. You can't expect an explosion of the space trash falling on Earth. Or they can fly away. Some of them can just fly away into space.
So, is there a telescope being designed to replace James Webb?
Yes, many. So every other year, basically, you find 3 or 4 satellite telescopes, proposals for satellite telescope, for space telescopes in Europe, in Canada, and in the US, which are the ones involved in James Webb. Not all make it through, but I mean the expected life of James Webb will be 5 to 10 years, hopefully a few more. So that means in 2032 we will not have James Webb anymore. So we have to plan. We are already building the next telescopes. Right now we are making the designs for telescopes that will be launched in the 2040 and 2050. So with 20 to 30 years. That's how long it took James Webb. So you have to plan ahead.
Amazing. Okay, so we have one last question, and this one's interesting. Are there any parts of the universe in which a photon will never reach your telescope?
Yes, everywhere. Yes, just think if I had again the laser pointer or a flashlight, depends on how I orient it, it will not come to me, right? So it happens. Yeah, we're probably not seeing many objects because we don't get their light, or even the light is blocked by something between them and us. And also there may be some objects really far away that existed at the very beginning of the universe, but the light didn't have time to reach us. So yes, we are missing lots of photons, and even the objects that we see emit light in all directions. So we are only seeing the photons that are traveling directly towards us. If they are directly in a different angle, we will just miss them.
Excellent. Well, I'm gonna bring Dr. Vasquez back in, and he's going to see if he has any questions and wrap us up.
No, I just want to thank Alvaro for this great opportunity to learn about the James Webb, and I really appreciate his time and effort to give this talk, and we are very happy to have him. Thank you, Alvaro.
It really has been a pleasure. It has been my pleasure. I love talking about my job, and of course to this kind of audience is my favorite. So yeah, it's really been a pleasure. Thank you.
Thank you. Thank you. Thank you.
this will bring us to the end of our live stream. We definitely want to thank again Dr. Labiano and Dr. Vasquez for making this event possible. Remember, if you're already registered as a STEAM Explorer, add a journal entry for this event to qualify for the daily prize drawing. If you're not already a STEAM Explorer, and then you can register for free at wsteamfest.org. You can journal this event and qualify again for the daily prize drawing. I also want to thank Woodlawn School for sponsoring ThemeFest and the members of the STEAM team who have worked tirelessly to make this possible, especially Shannon Blakely on the website and Lena Patel on social media. So have a good day and enjoy STEAMFest. Thank you.